All right, let's jump right into one of the most fascinating and honestly high-stakes engineering puzzles in the tech world today. We're talking about building the enterprise RAG brain. We're going to demystify exactly how tech giants like Microsoft, Google, and AWS are securely weaving powerful AI into their private, highly sensitive corporate data. I mean, how do you make an AI smart enough to know absolutely everything about a company, but safe enough to never accidentally email the CEO's unannounced strategy to an intern?
Okay, let's dive into this. Here is our blueprint for today. 1. The enterprise AI problem. 2. Two make-or-break rules. 3. Building the knowledge base. 4. Journey of a search query. 5. Generating the safe answer. 6. Trade-offs and trust.
Section 1. The enterprise AI problem. Why not just ask the AI?
So you might be wondering, why can't a company just plug a standard off-the-shelf large language model into their servers and start firing off questions? Well, because the stakes are just too high. If you ask a standard public AI about a deeply held corporate secret, an unannounced product or some private IT ticket, it simply doesn't know. It doesn't have access to your internal, ever-changing data. And worse, if it tries to guess, it hallucinates. In a corporate environment, a confident hallucination isn't just a minor annoyance, it is a massive liability.
To put it simply, think of a public LLM like taking a closed book test. It's relying completely on whatever it managed to memorize from the public web during its training. If it forgets, it guesses. Enterprise RAG, on the other hand, is an open book test. It doesn't rely on its memory at all. Instead, it securely reads through your private documents, wikis, and emails in real time to find the exact answer. And then, this is key, it actually cites its specific sources.
And that brings us to RAG, or Retrieval Augmented Generation. This is literally the ultimate fix for corporate AI. It's a system purpose-built to first retrieve relevant, private passages from your company's servers, and then condition the AI's generation process on them, basically forcing the AI to base its answer solely on those retrieved passages. This guarantees a grounded, cited answer instead of some creative fiction.
Section 2. Two make-or-break rules, high-stakes integration. For an enterprise RAG system to actually survive out there in the real world, it has to flawlessly execute two absolute, non-negotiable rules. The first is strict adherence to ACL, or Access Control Lists. This is the security protocol that dictates exactly who gets to see what. Think about the human element for a second. If ACL fails, an intern could innocently ask the AI about company strategy, and the AI might just pull context from the CEO's highly restricted emails to answer it. No way we can let that happen. The system absolutely must ensure a user never sees content they lack permission for, not even indirectly.
Now, what's really interesting here is these twin pillars anchoring our entire architecture: access control and groundedness. Pillar 1 is zero unauthorized data exposure, period. Pillar 2 is groundedness, which is how we combat hallucination using mandatory citations. Basically, if the AI makes a claim, it absolutely must point to the exact internal document that proves it.
Section 3. Building the knowledge base, the offline world.
Let's move to the build phase and see how this all comes together. Before anyone can ask a single question, we have to actually build the brain. We use connectors to constantly pull raw data from everywhere. Company wikis, Jira tickets, PDFs, you name it. All that raw data flows right into an ingestion pipeline that ultimately feeds into a massive vector database. This ingestion pipeline runs on a relentless three-step rhythm. Step 1. Parse. The system connects and reads the raw text, even extracting it out of really complex PDFs. Step 2. Chunk. It breaks these massive documents down into smaller, bite-sized semantic pieces, usually around 200 to 500 tokens. And finally, Step 3. Embed. It turns those chunks of text into complex math, vectors, and securely tags every single one with its specific ACL permissions.
To really grasp why this engineering is so mind-bending, you have to understand the sheer scale of it all. A typical enterprise has anywhere from 5 to 50 million documents. By the time that ingestion pipeline parses and chunks everything, you're looking at between 100 million and a billion mathematical chunks of data. It is a colossal, constantly updating mosaic of corporate knowledge.
Section 4. Journey of a search query, the online world.
Okay, so the database is built. The journey now starts the exact millisecond a user types a question. Instantly, that question zips over to the orchestrator. But it doesn't travel alone.
The orchestrator immediately attaches the user's specific access identity to the query. So, from the very first step, the system knows exactly who is asking and exactly what security clearance they hold. Next up, the system uses hybrid retrieval to search through those billion chunks, instantly filtering out anything the user isn't allowed to see. It casts a really wide net at first, grabbing the top 50 to 200 possible candidates. But, 200 is just way too much noise for an AI to read efficiently. So it passes those candidates through a reranker. This is a highly specialized model that violently narrows down those 200 candidates to find the absolute most precise 5 to 10 chunks of context.
Section 5. Generating the safe answer. The climax.
So here we are at the climax of the architecture. We've got our tightly filtered, re-ranked 5 to 10 chunks of private data. Now we bring in the AI. The LLM is handed the user's question along with those specific chunks. It generates the response, but, and this is the crucial point, it is forced by the system architecture to provide inline citations linking directly back to those specific chunks. Furthermore, if those retrieved chunks don't actually contain the answer, the LLM is strictly instructed to abstain. It literally has to say, I don't know, rather than trying to make something up.
But how do companies actually know this is working? Well, they evaluate it relentlessly. Engineers use a separate standards judge to test the whole system automatically. They measure groundedness to see what fraction of the AI's claims are perfectly backed by the context. They test context recall to make sure the retrieval system actually found the right files in the first place. They verify citation accuracy, and crucially, this is maybe the hardest metric of all to nail, they measure abstention precision. Is the system correctly saying, I don't know when it's supposed to?
Section 6. Trade-offs and trust. The architecture's reality.
Look, building a system that searches a billion private documents in 2 seconds without hallucinating, that isn't magic. It's engineering. And engineering is always about trade-offs. Architects are constantly balancing tensions here. Take quality versus cost. Sure, you could use a massive, incredibly expensive LLM, but a much smarter, more cost-effective approach is usually to invest in better retrieval and use a smaller AI. Then there's helpfulness versus safety. Users naturally want an AI that answers every single question helpfully. But corporate security demands an AI that leans heavily towards safety, meaning it has to abstain whenever it isn't 100% sure, just to prevent hallucinations.
And here is the big industry secret that basically defines this entire architecture. Most RAG failures are retrieval failures, not generation failures. Think about it. If your search pipeline doesn't retrieve the exact right internal document, it really doesn't matter if you have the smartest, most expensive LLM in the world, it's either going to fail or it's going to hallucinate. The real magic here isn't just the AI, it's the search.
Which leaves us with this final, provocative thought. As we rush to connect our most sensitive, sprawling corporate data to AI, the ultimate measure of an intelligent system isn't just what it knows. It's whether your architecture is rigorous enough to guarantee the AI knows when to simply say, I don't know. Thanks for joining me for this explainer, and I'll catch you next time.